So in today's lecture, I am going to prove the second isomorphism theorem along with the third isomorphism theorem. So you all can take down the second isomorphism theorem. If K is less than G, that is K is a subgroup of G. Okay, if K is a subgroup of G and N is normal subgroup of G, then you all have K upon K intersection N is isomorphic to Kn upon N. Okay. Now moving towards the next part, that is, let us start with the proof. Okay, what we need to prove over here is this: K upon K intersection N is isomorphic to Kn upon N. This is what we have to prove. Okay, so let me start. Proof: since K is less than G and N, this is a normal subgroup of G. Now it implies that Kn is a subgroup of G and N is normal in Kn. Okay. Now since N is normal in Kn, we define, since your N is normal in Kn, we define this. So basically what we do is we take the left coset. So we define Kn upon N is equal to Kn, this is small k, okay, small kn into N, where this small kn belongs to capital Kn. Okay. So for small kn, N, where Kn belongs to Kn. Okay. Now this is equal to what? Kn, where this k belongs to K. Small k belongs to capital K. It is. Okay. Now moving towards the next step, that is this. So define an onto map. So what we have to do is we have to define it. Now we need to check if f is okay. So define an onto map. Okay, f from K to Kn upon N such that f of K is equal to Kn for all K belongs to capital K. This is small k belonging to capital K. Okay. Now we need to check if f is well defined. Okay. Now we need to check if f is well defined. Okay. Now to see if f is well defined, right? F is well defined. So there is a condition, right? So K1 is equal to K2. Now this implies that K1 into N is equal to K2 into N. Okay. Now this implies f of Kn. Why? Because what is Kn is equal to f of K. So we are using this over here. So it will be f of K1 is equal to f of K2. So now this implies that f is well defined, right? So now moving towards the next part, now we have to see if f is homomorphism. Okay. Now we have to check that if f is homomorphism. Okay. F is homomorphism. Now to see f is homomorphism, what we need to do is f of K1 K2 is equal to K1 K2 into N. Now take K1 into N and K2 into N. Okay. Now what is this? What condition we are using over here? We are using the condition this: f of K is equal to Kn. So f of K1 of N is equal to f of K1. K2 of N is equal. This is f of K2. Now this implies that f is homomorphism, right? Now by fundamental theorem of homomorphism, what we do is, I hope you all can see. So okay, let me read it one more time. By fundamental theorem of homomorphism, K upon kernel of f is isomorphic to f of K, which is equal to Kn upon N, right? Now what is k upon kernel of f is isomorphic to, we can write this kn upon n over here because this is equal to this, right? So what we do is we write k upon kernel of f is isomorphic to kn upon n and take it as equation 1. Okay, now what we need, we have, okay, I hope you all can see this clearly. Okay, let me. Now to show that kernel of f is equal to k intersection n. Now what we need to show that kernel of f is equal to k intersection n. Okay, because we got this part. Okay, the statement of the proof you all can see. We need only this kernel of f to be k intersection n. Okay, now we need to prove that. Now k upon kernel of f is isomorphic to kn upon n. This is some, okay, this is what we have as equation 1. But before that we need to prove that f is onto. Okay, now we have okay, so we have to show that f is onto. Okay, for any y belonging to kn upon n, okay, there exist k, small k belong to capital K, such that f of k is equal to y. Okay, so this what is f of k is nothing but kn, right, is equal to k dash of n. Kn is equal to k dash of n. Now this implies that, now what I have done is over here is I have taken this k to the other side. So k dash, k inverse k dash belongs to n. Now this implies that this k dash, okay, it belongs to kn. So k inverse, I have taken it towards the right side, so the inverse will go, right? Now this implies that k dash is equal to kn. This is small kn. Okay, now for some n belongs to n, capital N. Now this implies that k is equal to k dash into n inverse. Now this implies that f is onto. Okay, now we got, now we can see that f is onto over here. Okay, now we have to show that kernel of f is equal to k intersection n. Okay, so what we need to do is, so we take the element over here first. Okay, so take the element x which belongs to kernel of f. Now this implies that f of x is equal to n. Now f of x is nothing but what? It is xn is equal to n. Now this implies that x belongs to n. Okay, f of x is given by xn. Okay, here f of x is given by xn which is equal to n. Now this implies x belongs to n. Now since kernel of f is less than k, it implies that x belongs to k. Okay, you all can take down this part. Okay, then I'll move forward. Now this implies that x belongs to k intersection n. Okay, now therefore kernel of f is equal to k intersection n. Now this is because kernel of f is a subset of k intersection n. Okay, now we write x belongs to k intersection n. Now what is x belongs to k? Now x belongs to here kernel of f. So kernel of f is equal to this k intersection n. Now you all are using the using in equation 1. Okay, you all are using this in equation 1. So what you will get in place of what you all have, so in place of kernel of f, what you all are going to write? K intersect, because kernel of f is equal to k intersection n, we have proved. So k upon k intersection n is isomorphic to kn upon n. Okay, so okay, note, if G is finite, then order of kn is equal to order of k into order of n upon order of k intersection n. So we have written this in this form. Okay, So basically what you'll have to know is, so we are done this theorem, that is second, we are done with the second isomorphism theorem. Okay, now what we are going to do is, we are going to do this third isomorphism theorem today. Okay, so the statement of the third isomorphism theorem is, if m comma n, okay, like if m and n is normal in G, if this m and n is normal in G and n is less than m, that is n is a subgroup of m, okay, then G upon n upon m upon n is isomorphic to G upon m. Okay, this is what we are going to prove in this. Okay, we have to prove this theorem. Okay, this third isomorphism theorem we have to prove. Okay, this is the statement. Okay, and we need to prove this, that this is isomorphic to this. So let me start with the proof. Okay, now since m comma n is normal in G and n is a subgroup of m, we are going to define G upon n and m upon n comma G upon m. So what we have to do is now define an onto map. Okay, that is f from G upon n tending to G upon m such that f of Gn where Gm. Okay, so now what we have to do is, now to check if f is well defined, now we have to see if f is well defined. Okay, and this is the condition which is given to you all. Okay, that is f of Gn is equal to Gm. Okay, now let us see. Now f is well defined. Now G1 of n is equal to G2 of n. Okay, now this implies that G1 inverse G2 belongs to n since n is a subgroup of m. Okay, now G1 inverse into G2 belongs to m, then G1 m is equal to G2 m. Now what was the condition? G m is equal to f of Gn, right? So f of G1 of n is equal to f of G2 of n. So from this we can see that f is well defined. Okay, we can see that f is well defined. So moving towards the next part, that is, now we have by fundamental theorem of homomorphism. Okay, now we have to see, by fundamental theorem of homomorphism, G upon n upon kernel of f is isomorphic to f of G upon n. Okay, so now since f is onto, okay, now we have to show that f is onto basically. Okay, so let us show that f is onto. For that, what is the statement? For any y belonging to G upon m, there exists Gn belonging to G upon n such that f of Gn is equal to y. This is the statement. Okay, now we have to, taking this, we have to prove that f is onto. Okay, now Gm is equal to G dash of m. Now this implies that G dash into G inverse into G dash belongs to m. It implies G dash belongs to Gm. Okay, so what I have done over here is I have taken G inverse to the other side, so it will become positive, right? The inverse will go. Now G dash is equal to Gm, small gm, for some small m belonging to capital M. Okay, so now this implies that this G is equal to G dash m inverse. I have taken this m to the other side, so it will become m inverse. Now this implies that f is onto. Okay, now image of group is equal to codomain, that is f of G upon n is equal to G upon m. Okay, now so G upon n upon kernel of f is isomorphic to G upon m, and take this as equation 1. So we have to show that kernel of f is equal to m upon n. Okay, now we have to show that kernel of f is equal to m upon n. So in place of kernel of f, what we need is m upon n. Okay, now we have to show that. So now to xn, now to show that kernel of f is equal to m upon m, let us take an element xn is belongs to kernel of f. Okay, now this implies that f of xn is equal to m. Now xm is equal to m, xm is equal to m. Now this implies that x belongs to m. Now xn belongs to, now this implies what? Xn belongs to m upon n. Therefore now this xn is belonging to what we have done is, wait, okay, now this xn, it belongs to kernel of f. So in place of xn I am going to write kernel of f over here, okay, which is equal to mn. So therefore kernel of f is equal to m upon n. Okay, so this was m upon n. So now using in 1, so we are putting this value of kernel of f is equal to m upon m. We are plugging this value in equation 1. Okay, so what is your equation 1 over here? Okay, g upon n, in place of kernel of f I am plugging m upon n. Okay, is isomorphic to g upon m. Write it as it is. Okay, this part. In place of kernel of f I am writing what? M upon n. Okay, so finally we have proved the third isomorphism theorem. Okay, I hope you all have understood the second isomorphism theorem and the third isomorphism theorem, which I have already proved. Okay, and thanks for watching.